Welcome back. Let's continue from where we stopped, looking at some past questions regarding our topic, which is standard separation techniques. Which of the following is an example of a mixture? Bonus question. Very bonus. All right. So the right answer here is blood. I know you might say, okay, why sand is not a mixture? Sand contains some chemical, all right, that you can really tell their chemical formulas. Sand contains silicates, but blood, there's no chemical compound. So blood is a typical word mixture, not sand. But don't go for sand because these two can be used. If there is no blood and they put another chemical compound here, you can go for sand. But if blood, something like blood, like air, and we have sand, don't go for sand because sand contains a chemical, all right, that can show their chemical formula. So the answer there is what? Is blood. Which of the following substances is a mixture? Okay, another one comes here. Sulfur powder is not a mixture. Distilled water is not a mixture. Ethanol is not, but the answer is what? Is B, bronze. Bronze is an alloy, so it's a mixture of copper and what? And tin. All right. Okay, so we move over to the next topic, which is periodic table, the last topic for this episode. So we're going to look at the features, the blocks, the families, properties of elements, and their diagonal relationship. All right, so this is a typical periodic table. So I'm going to explain so many things from here. You listen attentively before you get to the notes. All right. So this periodic table is a systematic arrangement of elements based on their increasing atomic numbers. You can see from 1, which is hydrogen, down to 103. Okay, so they are placed based on their specific property. They don't behave the same. Just like in a family, we have a group of people. We have the fair people, the dark people, the tall and the short, grouped in the same place. That's how it is done. So elements of the group 1, okay, contains 1 electron in their valence shell. That is why they are placed under group 1. Okay, this is your group. We have 8 groups. This is your group. Your horizontal line, your vertical line is your group. Horizontal axis is your period. So we have 8 groups. Group 1, group 2. According to the modern periodic table, we have group 1. We have group 1. This is group 1. We have 2, 3, 4, 5, 6, 7, and group 0, or you call it group 8. Okay, so elements that contains valence electrons of 1 are all placed in group 1. Element that contains 2 electrons in their valence shells are all placed in what? In group 2. Elements that contain 3 electrons in their valence shells are in group 3. Same to group 4, 5, 6, 7, and group 0. Group 0s are called noble gases. Why? Because they have a complete octet electronic configuration. They are not reactive. They are not getting it. They are not giving out. They are not collecting. So they are comfortable. That's why they are called noble gas or group 0. All right. If you are drawing electronic structure for group 8 elements, you notice that, for example, let's use neon for example. This is neon. Neon has what? 10 number of electrons. The first shell contains 2. The air shell contains what? 8. By their structure, okay, notice that this neon is completely balanced. Okay, you can see it's completely balanced. So 2 at the K shell, 8 at the L shell. Same thing happened to what? To argon, to krypton, xenon, and so on and so forth. So they are stable, they are comfortable, they have their complete octet configuration. Okay, unlike every other element, okay, that can either collect to be balanced or donate to be balanced. So elements of group 1 are known as what? Are known as alkaline metals. Alkaline metals. Elements of group 2 are known as what? Alkaline earth metals. Okay? Elements of group 7 are called the halogens. This is group 7 elements are called the halogens. While the elements of group 0, of course, I said before, they are called what? The noble gas. Now, in between group 3 and group 2, we have what we call the transition metals called the D block. This is the D block elements, meaning that their configuration ends at D. Okay, so from scandium to zinc and so on and so forth are what the D block element called the transition what metals. We have what we call the inner transition metals, which is from what? From atomic number 57, okay, down to what? 71, which is called what? The lanthanide, and the other one is called what? The actinoid. All right, lanthanide and what? Actinoid what? Elements. Is that okay? So if you look at the colors, this is the key to the periodic table. You can see now, all of this is these alkaline metals. All of this is called what? Alkaline air metals. Then all this purple color is known as what? Transition metals. Then others. Okay, these are other metal. Then other non-metals, which is this. All right. Then the halogens, group 7. The noble gas, white in nature. Then the rare gases and so on. So you can see, the being was systematically what? Arranged. They are not scattered. Okay? All right. So, the next slide will tell us some. All right. So, these are some of the features. I will not read it for you. So, just go look at it very well. I said some of this thing before. Okay? When elements are what? Systematically arranged according to what? Their increasing atomic number. Okay? And the basis of assumption behind this periodic table is because of what? Their periodic law. We state that the properties of the element is what? Are a periodic functions of their atomic number. That means that whatever happens in periodic table comes from where? As a result of their atomic numbers. Result of the what? Of their atomic numbers. Whether they are non-metals, they are gases, they are metal, okay, because of what? What are the number of protons and electrons present in that atom? That is what gives them their properties. So that's what they call what? The periodic law. We state that the properties of elements are what? Periodic function of their atomic numbers. Okay, what are some other features? I said before, we have 8 groups, okay, and 7 periods. The horizontal is called what? The period, while the vertical is called what? The group. Elements in the same group have the same number of electrons in the outermost shells of the atom. I said that before. Elements of group 1, valence shell of group 1, group 2, valence shell of group 2, and so on and so forth. All right, so this thing I've said that before. Go through the slide very well. The note is not much. It's self-explanatory. Okay, now these are the rules of assigning what? Their charges. Otherwise known as what? Oxidation states. Okay, so for group 1, 2, 3, and 4, 0, their group numbers are their what? Are their oxidation state or charges. Don't forget. If the element belongs to group 1, it has a charge of +1. For example, lithium, sodium. Okay? For example, we have lithium. In this case, for example, group 1, sodium is in group 1. Okay, charge of +1. Lithium is in group 1, charge of +1. If you go for a group 2 element, example, magnesium, +2. We have calcium, +2. If you go for group 3, we have something like aluminium, which is +3. Okay, then for group 4, we have copper. Then for noble gas, we have neon. Okay, we have xenon, and so on and so forth. So their group number are their what? They are exactly what? Oxidation states. Then for groups 5, 6, and 7, how do you get their charges? You subtract their group number from the noble gases, and you get their charges. For example, for group 5 element, we have nitrogen. That's why you always have nitrogen as what? As 3-. Okay? Because nitrogen is in group 5. So it needs 3 electrons to complete its octet nature. So you have to borrow from 3 electrons from the metal and complete its octet. Elements of group 6, example, oxygen. What do you do to that? It has 6 electrons. So subtract 6 from 8, you have what? 2. That's why you know how you always have oxygen as -2 has a charge. What of element of group 7? Example, fluorine, chlorine, bromine, and so forth. So 7 minus 8 gives us minus 1. Okay, so these are all non-metals, and most of them are gaseous elements. All right, so don't forget, for groups 1 to 0, their group number is their oxidation states. Then from group 5 to group 6, you subtract their group number from 8 to get their what? Oxidation states. Group 6 minus 2, group 5 minus 3, group 7 minus 1, group 0 is 0. All right. Then for transition metals, they have varieties of what? Of states, okay, because of their electronic configuration. For example, iron is a transition metal. Iron can exist in +2 and also in +3. We also have example manganese. Manganese can exist in +2. It can also exist in +7 and so on and so forth because of the tendency to lose their valence electron. This is not today's class. Maybe next time I'm going to talk more on what transition metals. Okay, let's look at some other elements. Elements in the same period have the same number of electron shells. Yes. For example, period 2 contains 2 electron shells all through the elements. Period 3 contains 3 shells all through, and so on and so forth. Number of valence electrons of elements in the same period increases progressively by 1. e.g., for example, if I want to start with let me start with the first one. For example, this is hydrogen. Hydrogen is the first element with atomic number 1. Now this is a period 1 element. The next one is what? Is helium. Atomic number 2, you can see by what? Addition of 1. If you go to period 2, we have lithium. Alright, lithium has what? Atomic number of 3. Alright, followed by what? Followed by beryllium. Okay, atomic number what? 4. Followed by what? Boron, 5, and so on and so forth. If you come to group 3, you have what? Sodium, 11, followed by what? Magnesium, 12. So they increase by 1 progressively across the period, okay, till you get to the last element. That's why period table is a systematic arrangement, okay? All right. And we also said that the number of valence electrons, I said that before, in period 5 and 6, the elements of the lanthanide and lanthanide series are present respectively. They are collectively known as what? The inner transition metals. Okay, fabulous. I said that before. Group 1, alkaline metals. Group 2, alkaline earth metals. Group 7, halogens. Then group 0 are known as what? The noble gas. Don't forget that elements of the same group, okay, have the same chemical properties. Have the same chemical what? Properties. Don't forget. Because of what? Because they have the same number of valence electrons. So the elements in group 1, group 2, group 3, and so on, they behave the same chemically. But they may have different physical content. Maybe out their softness, their density, their colors. When you come to their reactivity, they are the same because of what? They have something in common to all of them in that particular group. All right. So group 1 and 2 makes up the S block element, as I said that before. All right. Then group 3 to 7 and 0 make up the P block elements. Transition metals in between group 2 and group 4, group 2 and group 3, give us what the D block. Then the lanthanide and the actinides, okay, are the inner metals that give us what? The F block in the periodic table. Now, if you are going by electronic configuration, okay, so all the S block contains 2 electrons maximum. For example, if I want to write the electronic configuration of, let's say chlorine, will give us what? Atomic number 11. The first shell is 1s2, okay? 2s2 followed by what? 2p what? 6. You can see now, the S contains 2 maximum, the P contains 6 maximum. As you're counting, you're looking at it. 17. We have taken what? 10. So how much is remaining? 7. So what should be the next shell? Next shell is 3s, which is 2. Then the last shell is 3p. 3p what? 3p 5. So if I pick another element that up to like 30, I will get to D and get to F. So all the S contain 2 electron maximum, don't forget. All the P contains 6 electron maximum. All the D contains 10 electron maximum. And all the F contain what? 14 electron maximum. Okay, so let's go for a brief break. When we're back, we'll continue from there. Just stay tuned.